All right, you guys, our last video, finishing up this final exam review. The majority of the remaining questions are all about exponential functions. So remember, exponential functions are either continuous growth or continuous decay, right? And so they're gonna have that asymptote and all that good stuff. All right, so our first one is asking us to just do domain and range again of the exponential function. Right, and so you're just, again, looking for that wall, basically. So notice this one has a solid dot on the end, so it doesn't have arrows going both directions like a typical exponential function would. So when we are doing our x values, right, we know he's trying to go forever left, but something has stopped him at that black dot, right? And that has an x value of -2, but it's going forever to the right from that point. So that means our domain is going to be, here I'll put a D for domain, x is everything greater than or equal to -2. And then of course we have our range, right? So he's trying to go down forever and ever and ever, but he can't because he hits a wall at that solid dot. And hold on, let me get a little smaller with my highlighter there. It's pretty thick. All right, so there we go. Better. All right, so there's our wall, and that looks like it has a y value. I'm going to assume that that's 4.5. So our range is all the y values that are greater than or equal to 4.5, right? Because it's that and everything up. All right, looks like this next one is kind of a real world scenario, talking about population over time. So some city is growing exponentially here. Now, the first thing I notice is that it's definitely a solid dot right there. I know the dot's not drawn, but we assume that that's where our graph starts, and we're not going back in time. So we're just gonna kind of eyeball what that point is. So it's obviously somewhere between 200,000 and 300,000. If you wanna say that's the midpoint, you can. To me, it looks like maybe a little higher. So I really don't care what number you give to that. 250,000, 260,000, that is totally up to you, right? I'm gonna say 260, because to me it looks a little more than halfway, but I would take any number there. I wouldn't count that wrong, just because you have to kind of guesstimate what that value is. All right, and so then of course that means our domain, right? So here is, for the x value, we're starting at 0. So x is everything greater than or equal to 0. Right, if you need to. Here, there we go. Right, so here's that wall for the x's. So that's where our x value of 0 is. And then of course our y value, right, is that starting population, right? And so our range is going to be y is everything greater than or equal to, and I'm saying 260,000 people. All right. These next two questions are going to be exponential functions, clearly, but you're probably just going to want to put these in Desmos and run a regression. Clearly, I can see the starting point in this table is 18. But I'm not going to really assume or figure out what that growth is by hand. So you certainly can if you want to. Remember, the formula for an exponential is y equals ab to the x. So when you do that in Desmos, remember the regression is going to be y sub 1 is approximately ab raised to the x sub 1. All right, so I'm going to go to, sorry about that. I'm going to go to Desmos, and I'm going to add a table and just do a really quick little regression here. So -2, -1, 0, 1, 2. And this is clearly a growth because we can see our table values are getting bigger and bigger as our x's are getting bigger. So we know it's a growth, and we'll be able to look at that graph too, 25.92. I'm gonna hit the home button here. All right, so you can kind of see the scatter plot going on here. It almost looks linear, right? But it's definitely got a slight curve to it. And so I'm gonna ask Desmos to figure out what exponential function best matches those 5 data points. So y1 approximately AB raised to the x sub 1. And as soon as I type that in, it looks like a perfect match curve, right? And you can tell that because that r squared. Anyway, so the A is 18 and the B is 1.2. Right, so 18 and 1.2. So I'm going to come over here. So y equals 18 times 1.2 to the x power. Right, and that is our answer. Right, so remember, just as a refresher, because we're about to talk about this in just a few seconds, remember, I know it's a growth because the b is greater than 1. So I'm just going to put some little notes here. And I know it's a growth by 20%, right? Because it's one, if I write that as a decimal, that's 120%. So we know it's a growth because everybody starts with their 100% of whatever they started with, and now it's 120%. So it's growing by 20% every time. Okay. All right, we're gonna do the exact same thing over here on this guy. So I'm gonna go back to Desmos, and I'm gonna go to my table. And let's see, 1, 2, 3, 4, 5, 6, 7, 8. And this is also another growth, clearly, because the y's are getting bigger. Oh, I'm so silly. I was not paying attention. I'm going to start over. It obviously doesn't have all 1 through 8. I was getting a little... 4, it skipped some, and I did not catch that. Oops. 4, 5, 7, 8. That definitely would have given me the wrong answer. All right, I didn't have enough y's to match. Okay, so 2, 6, 14, 28, 50, and 86. All right, I'm gonna go kind of do the table. Now this one definitely looks like a scatter plot, right? I can tell there's not a perfect curve that's going to go through here, so I'm expecting that my numbers are going to be not as friendly at decimals as we got on the last problem. I just want to check my table though really quick and make sure I typed everything in correctly. Okay, that looks good. All right, so I'm going to go run the regression. So y1 approximately a b raised to the x sub 1. And yeah, definitely not as friendly of numbers as we got on the last one, which you can tell by the picture, right, that it is a scatter plot, right? So we are trying to find the best function that best fits. So I'm just going to say 2.6. I'm just going to round my a value to 2.6. And my b, I'm just going to say 1.55, let's say. If you want to write more decimals, you are more than welcome to. The more decimals you write, the more accurate your answer is going to be. All right, and so I'm going to write my function y equals 2.6 times 1.55 raised to the x power. All right, and that would be our approximate function. And again, I'm just going to throw in, because we're going to talk about this more in just a second, this is definitely a growth. And it's a growth by about 55%. Let me write about, because I definitely rounded to get to that 0.55, so about 55%, because as a percentage, this would be 155%. Oops. Okay. All right. Let's go read some scenarios and write our exponentials. So they're pretty much going to give you everything you need. I'm just going to do a quick little refresher at the top of the page here, even though we just talked about this. So remember, exponential functions are y equals ab to the x. Right? And the a is the starting amount, or your y-intercept. So it's how much you started with, right? The number of people, the amount of money that you put into account, the number of bacteria in a petri dish, right? And so whatever you're starting with. And then the b is 1 plus or minus the rate of either growth or decay. Right? So if you add the r, that's growth. And if you are subtracting r, which means you get a number less than 1 because you're subtracting the rate, then that would be decay. Okay? All right, here we go. A particular type of cell doubles. So that means doubles means 200%, right? I start with my 100% and it's now 200%. Every hour, write a function that can be used to find the number of cells present at the end of H hours if there are initially 4 of these cells. So initially being the starting number, right? So when we write our function, y equals, and our a value, I'm going to kind of color code this, is 4. And then in parentheses, it's going to be 2 because 200% as a decimal is just 2, right? Because you move the decimal 2 places to the left. And it says present at the end of H hours. If you want to write X up here, I'm totally fine with that. The problem says after H hours, so they're using H. So I would prefer the X, but I'm just going to cross that out and put X right there. But if you put an H, obviously that is what they're intending for you to put there. And that's it, right? They're not asking you to do any work or anything like that, just want you to write the function. All right, number 51. Sarah invests her graduation money of $3,200. That sounds like her starting amount. And it pays an interest, so that's automatically growth, of 12% compounded annually. All right, so this is growth. All right, write a function that can be used to describe her investment after X years. All right, so y equals her initial investment of $3,200. And then if you're growing 12%, please don't just put 12%, right? She still has 100% of her $3,200. So it's 1 plus the 12%, right? Her 100% plus the additional 12% growth. Right? And so when we write that in parentheses, it needs to be 1.12 to the x power, right? To show that she's getting 112% growth on her money because she's keeping the original 3,200 obviously the whole time, right? And that's the 100% plus the 12 more. All right, let me go back here. Number 52, there are 1,024 players in a tennis tournament. Okay, that sounds like an initial number. In each round, half the players are eliminated. All right, so half the players, right? So that's 50%. Write a function that can be used to find the number of players remaining after X rounds. All right, so pretty much the same thing. So y equals, we're starting with 1,024 players. We're reducing it by half. Now, technically, I just want to make this very clear. I'm not putting 0.5 here necessarily because of that 50%. I'm putting 0.5 there because I'm starting with the 100%, the 1,024 people, but I'm reducing it by 50%. So it's 100% minus 50%, which is 50%. Okay, so I'm getting that decay factor in there. Oops. And there's our function. All right, last one of these. The amount of fertilizer in a warehouse was originally 78,000 cubic yards. All right, that's our starting amount. It has a decreasing rate of 3% per week. Decreasing, right? So this is a decay. Write the function. All right, so y equals, we started with 78,000 cubic meters of fertilizer, and we are reducing it by 3%. So now you got to think about that. We have the 100% that we started with, but we're losing 3%, right? So it's 100% minus 3%. So what percent are we keeping? Well, 1 minus 0.03 is 0.97 to the x power. I do not put 3% in the parentheses, right? We put 97% because we have the 100% of fertilizer that we started with, but we're decreasing the amount of fertilizer by 3%. Okay, so that means we're only keeping 97% each week of the fertilizer that we started with. Okay. All right. These last couple are just graphs. You can totally just type these into Desmos if you want to, or you can do them by hand. That's completely up to you. I'll start off kind of doing a little bit by hand. First of all, the A value, let me go purple. This is the A value, right? So I know I'm starting, my y-intercept is 8, and I haven't shifted it up or down at all because there's no plus or minus on the end for any transformations. And then this is 0.25, which is definitely a decay because it's less than 1, and it's a pretty steep one, right? So I know my graph's gonna look something like this. I'm gonna go to Desmos though and type that in so we can get a nice, some accurate points. So here we go, 8, right, y equals 8.25 raised to the x power. There we go. And notice there's our y-intercept of 8. Oh, I didn't put 0.25. I'm like, why is it a growth? There we go, decay. All right, and so then I want to kind of find some other points. Right, so that guy right there, right, looking like, oh, I'm not in the right mode there. So I'm cutting everything by 75% and I'm only keeping 25%, right? So if I do 8 times 0.25, right, we get 2. I'm gonna go back here. Another thing you can do if it's hard for you to read the Desmos, you can totally do XY table and just do it by hand. These are just options. You don't have to do it this way. Obviously, I know when I put in a 0, I get 8, right? Because that's my y-intercept, right? If I put in a 1, right? Well, remember, these are my x values, so I'm putting them up here. So 0.25 to the first power is just 0.25 times 8, will give me 2. And then if I put in a 2, so 0.25 squared, and multiply that times 8, we get a half. And then we're just going to get smaller and smaller numbers until we start reaching the asymptote. So I'm just going to plot what I've got there. So 1, 2, and then 2, 1/2. Right, and so my curve is very sharp. And I knew it was going to be a very steep curve because the 0.25 tells me that we are declining at a rate of 75%. And I can kind of go up like that. All right, so now I should be able to answer the questions, right? It says, what is the y-intercept? Of course, 0, 8. The asymptote, right? Remember, the asymptote is the imaginary line that this function will never, ever touch. It's trying to get there and get closer and closer and closer forever and ever and ever. You can definitely tell where that is in Desmos because in Desmos, it's going to look like a perfectly horizontal line. So you can see it almost appears as if this is lying on the x-axis, but it's not, right? The more I zoom in, I can just keep zooming in more and more and more and more and go further and further. And you can see that this guy is actually not touching the x-axis, but to our human eye on this graph, it looks like it is, right? So that's the asymptote. Okay, so let me go back to here. So our asymptote is y equals 0 because that's the x-axis. It's a horizontal line. Domain, let me here. So domain, he is going to go forever left and right, because he is going to get wider and wider up here, right, just very slowly, right, and then he's definitely going forever to the right. And then range, of course, is not all real numbers because that darn asymptote, right, so my range is y is everything greater than 0. I can't use the equal to bar because I'm never ever going to equal 0 because that's the asymptote, right? So essentially whatever your asymptote is going to help you identify your range. All right, I'm going to pop over here and do this guy. Now, this one's interesting because of the -3 on the end, because it looks like my y-intercept is 2, because that's the A value, but then they added this -3 transformation, which means everything has been shifted down 3. So 1, 2, 3. So my y-intercept should actually be at -1. Now, I'm going to plot that in Desmos just so I can see all of that. And I'm going to make an XY table too. So 2... Let's see, I'm going to go back here. There we go. So y equals 2 times 4. So it's definitely a growth raised to the x. Let me go back over here. See, there's my y-intercept of 2, but then I put that minus 3 on the end, and what do you know? Our graph shifted down 2 units, okay? And notice where our asymptote is right here, right? It looks like it's at y equals -3 because normally it would be at 0, but the whole graph got shifted down 3, right? But notice it looks horizontal here, but it's actually not, right? I'm never getting there. So let's just go pick some points there. I've got 0, 1, 0.292. Yikes. All right, here we go. I'm going to go back up here. Okay, so we know our asymptote is at -1. If you want to make an XY table for this guy as well, you totally can. Our numbers are going to get pretty big pretty fast though. So just let you know. So if we do XY, so we know if we plug in 0, we get -1. What happens if we plug in a 1? So I'm just going to type that straight up into my calculator. So I'm going to raise it to the first power, which of course is just 4, and then -3. So I'm getting 5 because it's 8 minus 3. Now if I put in a 2, 4 squared is going to give me 16. So my number is going to be much bigger, right? So 2 times 4 squared minus 3. Yeah, that gives me 29, right? So the growth is going to be super big. All right, that's okay. So 0, 1, and then 1, 5. And then we know our asymptote is at -3. Trying to get that line. There we go. And that's enough points to help us get a decent looking curve, right? So it's a very steep curve because it's growing 400%, right? But then we're going to become asymptotic to that y equals -3 line, right? And then we should be able to fill in our stuff, right? So our y-intercept is 0, -1. Our asymptote is at y equals -3. The domain, of course, is all real numbers because he's going to go forever left and right. But because of that asymptote, its y is greater than -3 because the whole function is above our asymptote. There you have it. All right, the last page is just practicing graphing the 3 parent functions that we learned this year. This is on your final exam, and some of these you have to do by hand. So you want to make sure that you know your 3 parent functions. So let's just go through those really quick. Your parent linear function, I'm going to highlight. Actually, there we go. All right, so your linear parent function is f of x equals x, or y equals x. And if you forget, I'm like, well, you have to remember your parent functions, but then you can always put them into Desmos if you want to, right? So if y equals x, then that of course means I can make a very easy table, because if y equals x, then the y values are equal to all the x values, so I can just repeat them. And then of course, when I graph that, it's going to give me the parent linear function, which is just a perfect diagonal line splitting our coordinate plane in half diagonally. And then it wants us to define the x-intercepts, which is clearly 0, 0. The y-intercept is also 0, 0 because the line passes through the origin. The domain is all real numbers because he goes forever left and right. And the range is all real numbers because he's going forever down and up. Okay, so got to know that parent linear function. All right, next up is the parent quadratic function. All right, so f of x equals x squared, or y equals x squared, whether you put the f of x or y, I don't care. And so that means all my y values are my x's squared. Well, -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. And so when we plot these points, 0, 0, then my 1s, then my 2 4s, there's our nice pretty parabola. And I want an accurate parabola. Don't just slap some random, like just draw some U-shaped graph, right? We expect you to go through the actual points. Okay, that's a little wide actually, but that's okay. Actually, I'll fix that. There we go. All right, so just do the best you can. Remember, solutions, those are x-intercepts, right? That's another word for x-intercepts, just like roots and zeros, right? And so there's only one, so because it's going through the origin, which means our y-intercept is also the origin. The domain is all real numbers because he's going forever left and right, but the range is not all real numbers, right? Because he's hitting a wall at y equals 0. So y is everything greater than or equal to 0 is our range. All right, and then last but not least, we have the exponential parent function, right? This one is 2 to the x power. It's the most basic we can do. We just use a 2 for the base, or y equals 2 to the x, because we can't use a 1, because if I raised a 1 to any power, we just get 1 every time, and that would not be exponential. So we just use the next integer in line of 2 for that base number. So I'm going to take 2 and raise it to all of these x powers. And you can use your calculator for this, or you can just type it in Desmos. So 2 to the negative 2 power is a fourth. 2 to the negative 1 power is a half. Anything to the 0 power is 1. 2 to the first is 2, and 2 squared is 4. Right? And so I can plot those. Those 1/4 and 1/2 are really tiny, but that's because there's the asymptote. So our y-intercept is 0, 1, then 1, 2, then 2, 4. Let me zoom in there. All right? And then, of course, I'm going to go ahead and plot my 3/8 so I get that. And then it goes backwards and becomes an asymptote to the left. Getting closer and closer and closer to that x-axis, but never getting there. And then the zeros, again, remember zeros is just a fancy name for x-intercepts, right? And this has none, right? He's never going to touch the x-axis because of that asymptote, right? It doesn't ask us for the asymptote, but in parentheses, I'm going to write asymptote at y equals 0, right? So that's why there are no zeros, because he'll never cross that x-axis. His y-intercept is 0, 1 though. He does have a domain of all real numbers, but he doesn't have a range of all real numbers because of that asymptote. And so since he's above the asymptote line, our range is y is greater than 0. All right, please make sure you know those parent functions, right? They're going to pop up on your final exam a few times. Okay, so make sure you know your equations. All right, you guys. I hope all of that wonderfulness helps you out. And obviously, if you have any questions, always ask. Okay? See you guys soon.